Hi everybody, this is Kurt Munson from HBM nCode. I'm the engineering manager here, and this is part of a continuing webinar series about nCode software products. We're going to look today at the topic of ensuring full vehicle durability. How do we apply fatigue analysis concepts to very large models, for example, like the white body that we see in the lower right corner of the screen here. We'll be talking about this today over the next half hour or so, and we'll end with a software demonstration of how we use these techniques, put them into action to work efficiently with a very large model like this and still be able to understand fatigue in a time-reasonable manner. Our agenda for today is really three things. First, we're going to look at what makes full vehicle durability analysis hard these days. What's the challenge there? Why is this difficult? Or to put it another way, why do we need to talk about a solution? Let's talk about what the challenge is first. And then, having done that, we'll talk about the solution. What methods do we have inside nCode DesignLife software that we can use then to tackle this challenge of working with a very large finite element model and needing to understand the durability of the entire model. And then lastly, we'll wrap up today with a software demonstration. We'll have about half the time today looking at some slides here via PowerPoint, and the back half of the presentation we'll actually be using nCode DesignLife software live. And that way then you'll get a handle on how to put these techniques into action, and this is something then you can go off and work on your own. So what's the point of this webinar? Again, this is part of a continuing webinar series. So we have webinars on all kinds of different topics. This is not how to get started using nCode DesignLife or how to predict fatigue in general. This is something very specific. Today we're talking specifically about this topic of what techniques can we use to analyze the fatigue behavior of an entire model. So very specifically, this is not how to use nCode DesignLife. This is a specific niche of that. How do we optimize its use for working with a very large finite element model? We'll be looking at nCode software today, and if you're not familiar with it, let me just take a step back and introduce what nCode software is. nCode software is three components: DesignLife, GlyphWorks, and automation. And we have webinars on the use of each of these. We'll be focusing today on nCode DesignLife, which is a CAE-based fatigue analysis tool. In other words, building on the stress analysis you might do already with finite element analysis, for example, using Nastran or Abacus or ANSYS or Dyna. DesignLife will pick up with those stresses and then work to convert stress into fatigue life, how long until a crack starts. The other software products you see here, GlyphWorks and automation, are more focused on measured test data, say vibration analysis, strain gauge, durability work, and so on, and have been subject to previous webinars, so we'll leave those alone for now. We're going to focus solely on the nCode DesignLife product. As a matter of fact, we're going to focus on a very specific question today. How long will this last? Here we have a white body. It's probably a million or more elements these days. So if we're not careful, our calculation can end up taking a very long time. Solving the stresses using FEA in a very large white body like this can take a long time. We're going to look today at how do we make sure that we can apply intelligent fatigue analysis, but do it in an efficient way. If we're not careful, we can use a very powerful, fully featured fatigue analysis on a huge model and take a huge amount of time. Computationally, this can become very complex, can become very lengthy. So really the goal today is to answer the question, how long will it last, but also think about how can we do that quickly? How can we easily or efficiently analyze or answer this question, how long will it last? So what are the challenges? The challenges of full vehicle durability analysis. So we have a number of challenges, and this slide is very important because it really lays out what we're going to look at for the rest of today's webinar. We're going to have a challenge and look and see what solution does DesignLife provide to answer that. So let's get started from the top here. First challenge is we have a very large model. These days, a typical full vehicle or large structure model could be a million or more elements. So that's one challenge. How do we deal with such a large model? Second challenge is we may need to look at dynamic stresses. A lot of these structures, full vehicles, large structures and so on, oil platforms, vehicles, airframes and so on, can behave dynamically, which means then we need to be able to look at, say, dynamic stresses in FEA, a dynamic solution. That can take some time. So how can we efficiently use FEA and dynamics together, and then do the fatigue calculation accounting for that dynamics. We'll look at that in just a minute as well. Third one down, long loading sequences. What I mean by that is the time series data that describes how our part is actually used, the wave loading on an oil structure or the road loading into a vehicle frame. That can be many, many millions of time steps to really fully capture the variability of different drivers, different users, different weather conditions, and so on. So if we're not careful, we can end up with a lot of time steps that we need to solve for stress. So we need a better way of dealing with long time series. Fourth one down at the bottom, many proving ground events, not just long time sequences, but many different usage scenarios. Say, for example, different ballast conditions in vehicles, full of mass, half full, no passengers, that kind of thing. High-speed driving, low-speed driving, twist ditch, bump course, off-road, on-road, and so on. So we may have a number of different what we call proving ground events or road load data events that we need to look at the combined fatigue calculation, what kind of fatigue damage accumulates from all these different events. And then lastly, in the bottom left corner, we have to look at a fully featured, or some would say a complicated fatigue analysis in some cases. For example, if we have multi-axial loading or spot welds or seam welds. So we may need to change the fatigue model according to different types of structural attachments, for example. Spot welds and seam welds fatigue in different ways than parent metal, unwelded metal, and we need to account for that in our fatigue analysis, otherwise we won't get the answers right. So those are our challenges. Now let's switch gears here a little bit and think about solutions. And I'm going to illustrate each of these solutions in a slide, one slide for each of these solutions, and then we'll also look at them live inside DesignLife software in just a bit. So the first challenge was very large finite element model. So how can we deal with a very large finite element model? It's quite simple, to be honest. Let's analyze the important part of the model. So we're going to look at some stress results in a bit, and we'll see that, as you're probably used to seeing, looking at stresses tend to be concentrated in hotspots. And fatigue is like stress raised to a power. Actually, can be quite a large power. In other words, stress being concentrated results in fatigue being concentrated in the same area. So we can use this to our advantage and focus our fatigue calculations on areas of high stress. Rather than every area in the model, let's focus on the important parts. And you'll see we'll have some adaptive techniques we can use in DesignLife to make sure we find the right areas in an automated way. Secondly, very large model. What else can we do? Another solution is let's use CPUs and distributed processing to our advantage. It's very simple these days to do these analyses with multiple computing threads, and even now we see a trend towards multiple threads and multiple compute nodes using a HPC environment. So we'll look at how DesignLife has been optimized to work in these environments as well. Let's shift now and look at the challenge of dynamic stresses. How can we account for dynamic stresses in a complicated structure? Well, we're going to look today at how we can use what we call modal transients. So we'll look at using an FE solution that reduces the degrees of freedom by looking at modal transient analysis rather than direct transient analysis. And we'll see how this works in just a minute. Long loading sequences, all these time steps, what do we do with them? Well, there are ways you'll find in DesignLife that we can reduce the number of time steps to analyze. For example, we can focus on the time steps that are really fatigue critical, either because their load magnitudes are high or because of some cyclic nature. They're all the time steps in the time series. Some of them don't have anything to do with fatigue cycling whatsoever, or their magnitudes are quite small. So you'll see we'll have adaptive techniques we can use in DesignLife to reduce down the number of time steps that we analyze, focusing on the damaging time steps, or what we call the turning points, the peaks in the valleys that lead to fatigue cycles. Multiple proving ground events, what do we do? We're going to use Miner's rule, and we're going to use what we call a duty cycle. Some of you may refer to a duty cycle as a durability schedule or a composite or a mission profile. These are all the same words to say we have different ways of using our structure, our vehicle or our helicopter or our oil platform. And let's look at Minor's rule and weighting the damage contribution from different events according to exposure to those events. For example, with a car, we may have a proving ground mix or duty cycle or durability schedule that says we run through the bump course so many times and we drive on the city driving loop a lot more times. We're going to use Minor's rule with that to our advantage because Minor's rule just says that fatigue damage increases, accumulates, as more exposure time carries on. So we can be smart with this, and you'll see that in just a bit. And then lastly, the solution to these complicated fatigue analysis requirements is let's use lightweight but specialized fatigue analysis methods, specialized methods for dealing with spot welds, or for dealing with seam welds, or now for dealing with adhesive joints. So I'm going to look at each one of these solutions in a slide, and then I'll show you how they all work live inside DesignLife in just a minute. So remember these solutions on the right side to these challenges, and let's take an in-depth look at each one now. So starting with a very large model, how do we analyze only the important parts of a model? Well, if you've used DesignLife before, you might be familiar with this interface, this dialog that you see on the left side. This is what we call the advanced editor, or this is, you could say, the guts or the properties of the DesignLife calculation. And you can see here, actually, this has got 3 separate fatigue calculations going on, or even to be more specific, 1 stress assessment calculation, and then 2 fatigue calculations after that. And we can see those results in the graphs and the graphic displays on the right side. This particular calculation has what's called a stress assessment first. In other words, go find areas of high stress. Don't do anything related to fatigue first. Just go find areas of high stress, or to put it another way, get rid of areas of low stress. Then pass that list of high stress nodes or elements on to the next calculation, which happens to be a fatigue analysis. I call this a coarse fatigue analysis with what we call compressed or reduced number of data points time histories. And then lastly, do the calculation a 3rd time on an even smaller subset of the model, but use a really robust and fully featured fatigue calculation. So in this respect, then, I don't have to analyze the entirety of the model with a maybe computationally intense but technically correct fatigue model. I'm using stresses to discard areas of low stress, do a fatigue calculation on the resulting high stress areas or moderate stress areas, and then do a more complicated, more robust fatigue calculation that may take a little longer on just a reduced set of high damaged areas. We call this a detailed damage analysis in the critical areas, and that's what the 3rd run is. I'll show you how to set up these multiple runs inside DesignLife in just a bit. So this is one way we can focus on the areas of interest, reduce the number of hardcore fatigue calculations we have to do. Secondly, we can look at using multiple CPUs, multiple threads. DesignLife has been optimized to work with threads. You can see in this plot here, this is how much faster did the calculation run on the vertical axis versus the number of threads that were used. And we're at a point now where we get pretty reasonable scaling, quite linear scaling with increased number of threads. So we can easily take advantage of the threads that are available on just about every computer these days and find that calculation time goes down quite nicely as more threads are made available. Similarly, another twist on faster analyses these days in the CA world is to take advantage of multiple compute nodes, distributed processing, or what you might refer to as HPC, a high-performance computing environment. DesignLife is HPC ready. We can see here in this graph, similar plot to before, how much faster does the calculation run as a function of number of separate compute nodes that are being used. And you can see that we get very nice scaling with this. And keep in mind that this is a compounding effect because each one of these compute nodes will have multiple threads as well. So we can have huge time-saving effects in introducing threads and also distributed processing. Let's move on to the next challenge. One of the challenges was how do we deal with complicated dynamics of a very large structure? For example, in a vehicle white body, we might have 200 or more modes of vibration that we need to account for. We need to account for the dynamic stresses that arise from all of these modes. Now, if you didn't know any better, you might say, let's do everything as a direct transient analysis in FEA. The problem is that's computationally impossible, or very, very difficult, let's say, especially when working with large number of time steps as we've been talking about in this type of arena. So we're going to look now at how we could use modal transient analysis in FEA to best capture dynamics, but without relying on a direct transient. The idea here is we're actually going to run FEA twice. So up at the top, in the orange box, modal stresses. These are this is the eigensolution for stress. So in Nastran, this would be solution 103. Abacus is star frequency. ANSYS, this is a modal analysis. So this is stress per mode. And again, we might have 250, 300 or more modes that this is going to account for. We can run a second solution in FE, and that's the modal transient over here, solution 112, star modal transient, or a transient modal inside ANSYS. And that will then look at, it will come up with what we call the modal coordinates, which is in the time domain, how much of what mode is present. And that's what's plotted down in the lower left here. This is what's the contribution of mode 1 over time, what's the contribution of mode 2 over time. The beauty of doing this analysis, you might say, oh, now we've done 2 FEAs, but the beauty of this is that the modal stresses go very quickly. Modal transients aren't too bad either. The beauty of it is this, is that DesignLife allows us to assemble a stress history, which is a function of the superposition of these different modes. Modal stresses from FEA, modal transients, also solved from FEA, means DesignLife can assemble a modal superposition stress history. So now we've got dynamics accounted for. We've got a stress history that's got dynamics built into it, which means then we can go off and do the fatigue calculation and look at fatigue results while accounting for dynamics without having to solve F equals ma for all the degrees of freedom, since we're working in the modal domain here. All right, let's move on to the next challenge. We need to think about how do we reduce the number of time steps that we analyze. So here's a question for you. If this is your loading sequence in the time domain, this is loading versus time, do you think it's really important to include every time step in the damage calculation? Certainly large magnitudes are important to stress, which are therefore important to fatigue. Smaller magnitudes may not be contributing much to stress, which means their fatigue importance may be very low. And even further, there may be times in this time series loading here where the load doesn't even change. And if the load isn't changing, that means the stress might not be changing, which also means then that fatigue cycles aren't occurring. So there are time steps in this measured data that may not be important to us in a fatigue sense. Now, you may say, well, why was the data collected that way? That's because we have to use a high sampling rate, a high number of data points per second, to capture transients like this on the proving ground. Unfortunately, we also capture lots of data points when the loading is not transient, or the loading is not changing at all. So one of the artifacts of data collection is that we may have data points that are not important to us in a fatigue sense. So what we do then is we use a technique called peak-valley slicing. This will remove non-turning points or non-fatigue points from the loading time series. You can imagine it's a way of looking through this time series and saying, when does the load not change? If the load's not changing, if we don't have a localized peak or valley, then we're not contributing to a fatigue cycle, and therefore we may be able to get rid of that time step. And the less time steps we have to analyze inside DesignLife, the less time steps of stress superposition we have to do, and therefore we speed up the calculation. We can also include what's called a cycle gating option to remove small cycles. In the first description of this, I said, let's get rid of data points that have nothing to do with cycling, where the stresses or the loads are not changing. We can also get rid of times when the stresses or the loads are changing in a very small amount. For example, we may have very small cycles in here that are not important in a fatigue sense because, again, fatigue damage is proportional to the stress cycle size raised to a power, and it can be quite a large power. So a number of these small cycles can be omitted in the peak-valley slicing concept here to speed up, to further compress the number of data points that we actually need to analyze inside DesignLife. This is a really nice technique to work with multiple runs. We talked before about using adaptive techniques to rerun calculations, use smarter or more computationally intensive fatigue calculations on successively smaller parts of the model. This peak valley slicing works really well in that respect, and you'll see this being used in just a minute when we switch into looking at DesignLife Live. For example, we might want to put together a couple of fatigue runs inside our fatigue calculation. We might use an intermediate run with peak valley slicing to find the fatigue hotspots. But then you might say, hey, wait a minute, what if I omit cycles in doing so? Or what if I introduce this concept of a gate? Could it be possible that I'm throwing away important fatigue cycles, maybe very small ones, but what if it's possible that that produces some amount of fatigue damage that you need to account for? Well, the cool thing is we can set this up so that the intermediate run uses peak valley slicing to find fatigue hotspots, but then the final run that we do uses the time series data without any of this peak valley slicing whatsoever. So we're accounting for all possible fatigue cycles, but we're doing it on just the hotspots in the model, so we can afford to use a more computationally intensive fatigue calculation. So these two things work together very well, multiple runs and peak valley slicing. The benefit of doing this is that we're reducing the number of time steps to analyze, and ultimately then we're reducing calculation time, and that's the whole goal of what we're talking about today. So let's move on here. Let's think about, what if we have a bunch of different data files or events or different ways our customer, the end user, actually uses this thing, this structure, this vehicle, this airframe. I've got a picture here that shows a couple of different events. Event A, Event B, again, this might be high-speed driving, off-road, on-road, and an oil structure might be wind loading, wave loading, very severe storm, and so on. So it may be that the structure you're analyzing has different loading scenarios like this, or events, and it may even have a kind of a mix built into it to say that the average vehicle is driven through the potholes not very often, and on low-speed roads very often. So we have these events and also these repeats, different numbers of repeats that we have to associate. So some people call this a duty cycle. Some people call this a durability schedule, a composite, a mission profile, lots of different terms for this. You could kind of think of it as the recipe card for how is this thing actually going to be used over its full life. Now the beauty of this type of calculation is that we're going to use Miner's rule to our advantage. Just as a reminder, Miner's rule says that fatigue damage from different fatigue cycles is cumulative. It adds up. It's kind of like damage to your bank account. All the different ways you spend money all hurt your bank account, and it may not be one thing you do that's going to make you broke, that's going to deplete your funds. It's the summation of all of them together. It's the summation of the damage to your bank account that will lead to your brokenness. Likewise, Miner's rule says fatigue damage adds up. So we're going to use that to our advantage. DesignLife has Miner's rule built into it, and it has what we call a duty cycle mode that I'll show you in just a minute that will allow us to calculate damage for event A and then scale it up by a factor of 510. There's no reason for us to work with 510 repeats of this time series, calculate fatigue damage. That's going to be very slow. A better way, a more intelligent way, is to calculate the damage from one of these proving ground events and then increase it by the factor of how often is it used, and then further add to it the damage from 200 repeats of event B. So we'll see this being used live in just a minute. Now the last challenge and benefit before we see that live stuff is using specialized fatigue analysis methods. For example, this model here is a part of a white body, and it's got a seam welded construction, or actually a spot welded construction in this case. And we need to then understand that fatigue of the parent metal around the welds is fundamentally a different beast than the fatigue of the spot welds themselves. So what we want to do, and what DesignLife is capable of doing, is being able to apply specific fatigue methods to these different joining techniques. In this way, we can use a lightweight FVA modeling technique. For example, with spot welds, we end up using rigid beams to represent the interface of the two sheets. And we look at forces and moments that are carried by those spot weld beam elements and so on. And the key is that we can put some very fully featured or complicated specialized fatigue analysis methods into our calculation without relying on an entire remodeling or reanalysis of the entire structure. Here's some examples of ways we can improve or benefits, you could say, or time benefits, time comparison of using these techniques. This model was actually quite small. It was 18,000 elements, 40 time series events, about 1/3 of a million time steps that had to be analyzed. If we use this as one single run calculating fatigue for all elements, we end up with a calculation time of about 12 minutes, which doesn't sound bad, but if you were to work with a full white body, you'd have obviously probably 2 orders of magnitude more elements to deal with, so computation time becomes quite serious. So we looked at using 2 runs here. We'll use a 2-pass analysis. Let's do a quick and dirty damage calculation on the entire model, and then pass some percentage of the model onto our second run to do a more detailed fatigue analysis. And you can see then we've massively reduced the amount of time required. So using these you could say preliminary passes to find hotspots can be a huge time saver. And then you can see actually the third one we did here was we added a stress filter. You'll see how this is used in just a minute. So actually a 3-pass, and you can see that we saved even more time. And the beauty of this is we're still finding the correct critical hotspot and still getting the fatigue damage calculation right as well. So with that in mind, we can say see ya to PowerPoint, and let's go over and take a look at DesignLife now. How do we actually do these calculations in the real world? So this is not an introduction to how to use DesignLife. We've had other webinars on that, so I'm hoping that you guys have seen some of DesignLife before. What I'm going to do here is just very quickly put together a process where I'm going to analyze a finite element model. This is a small model. We'll look at a body in white in just a minute, but I'm going to use a smaller model so this webinar doesn't take a whole lot of time. I'm going to use some time series data here. And so this is the component of interest. This is the loading that we want to associate with the stress solution in FEA. And this will cause stress cycles. So let me just pull that together into a fatigue calculation glyph. I'll use a StrainLife glyph, which has lots of neat features in it for looking at plasticity corrections and cycle counting and all sorts of neat stuff like that. And I'm going to put a display on the end of this here so we can look at the answers when they come out. I'm setting this up kind of quickly, but again, like I said, the goal of this today is not to teach you how to use DesignLife, but rather to look at one specific aspect of DesignLife. Actually, I need to associate material properties here, so let's do this. I'm just going to associate a fatigue curve very quickly to say this is a monolithic shaft made out of this certain type of low-carbon manganese alloyed steel. And let's just let this run. It's got 3,800 elements that it's going to go off and process now. You can see it's working its way through them. Each one of those elements, it's got to look at superimposing these loads to create a superimposed stress history. So the stress history for each element or each node will be a function of the loading that's applied to them and the stress solution that came from FEA. So again, now this is analyzing the entirety of the model, and when it's done, you can see now here is our fatigue damage plot for the entire model. I'm just going to change this into fatigue life plot instead. Just bear with me a second here. We'll look at fatigue life instead of damage. It's just the reciprocal. So it's predicting down here that the fatigue life is about 190,000 repeats of this time series to failure. Now, that process ran reasonably for me. It's not a crazy big model. If it was a big model, it would run quite slow, and that would be a bummer. So let's start thinking about ways we can accelerate this using the techniques we've already talked about in this webinar. First off, look at all that blue in that model. Why are we using a fully featured fatigue calculation when really what we're really after is we could probably focus our fatigue calculation in the hotspots in this radius here. So let's dig into this fatigue glyph and make it a little bit smarter. So if you dig in here, we have, this is the fatigue engine right here. This is how the fatigue calculation actually happens. So it's using various parameters, various inputs that I've given it to say, here's how I want fatigue to be done. But it's doing it on the whole model, which is fine, but computationally expensive. So instead, I'm going to come here and say, you know what, rather than using the entire model, I want to add what's called an auto-elimination setup. This is going to add a run for me. It's going to add it's going to add a precursor to this fatigue calculation that's going to go find areas of high stress. So I want to do this auto-elimination based on stresses. Okay, so look at the stresses in the model. And let's say what percent of the model we want to keep. Let's keep say the top 40% highest stressed nodes, and then only do the fatigue calculation on those. So right off the bat, I should get rid of about half the model here very quickly, just based on stress, and then do a full fatigue calculation on the remaining part of the model. Let's say finish this, and we now have something in here that says, let's go off and find out what part of the model is really critical. I'm going to rerun this now. It's going to run a little bit faster. Notice it says it's got 2 runs here now and a smaller number of nodes to work on. And when this calculation is complete, you can see now that it's not bothering to do fatigue calculations in all those blue areas. Any area that comes back gray means no calculation was performed. So now we know for a fact that we have a really nice fatigue calculation being done, fully featured with all the time series data and stuff in this particular area here, right there. Okay, so that's one way we can speed up the calculation. Next way is we looked at these loading histories before and said, is it really important for us to do this calculation, the superposition of stresses, on every single sample data point in the time domain? Some of these loading points don't contribute to fatigue either because their magnitudes are small or because their magnitudes are not changing and the stresses may not be changing, which means the stress cycles are not happening. So we're going to introduce now this idea of peak valley extraction or peak valley compression. So let's dig back in here and get back to where we were previously. I'm going to say in my fatigue calculation, I want to use what we call a method of time history compression. And as a matter of fact, it was set to none before. In other words, take every single time step that I provide this fatigue calculation. This time I'm going to speed things up a bit further by using a peak valley concept. And I can even introduce a gate here which says I want to gate out anything that's not a fatigue peak or valley. And even further, I might want to gate out peaks and valleys that are quite small. So I can use this concept of gating here to even further speed things up. So we run this now. It's going to work through the same hotspots as before. Let's look at the full model here again, like this. So it's going to work through the full model again. The difference is that now it's not working with the full time history. It's being smart about what data points it needs to actually superimpose stresses from in the time domain, such that it doesn't waste its time looking at combined stresses if they're not changing, or if those combined stresses are quite small. And I said before that one of the interesting uses of this concept of peak valley extraction is that I can use this really efficiently in multiple runs. And you'll see how we do that in just a minute when we go to look at the full body analysis that was put together previously. The last thing I want to look at here now is how do I deal with multiple proving ground events. So I've been looking at fatigue under this loading scenario. Maybe this is the high-speed track. But what about the bump course and the potholes and the sitting and idling or the drag strip launch or something like that? So I have all these different events. So what I want to do now is use Miner's rule and a duty cycle, or what you might call a durability schedule, to my advantage. So instead of having one time series here, I'm going to go back in and change the way the loading is being provided for fatigue. And this time, rather than using time series data, I'm going to use what we call the duty cycle. Duty cycle. And it says, okay, so what duty cycle do I wish to work with? So I'm going to go browse, and I'm going to pick up this duty cycle over here, like this, pull that in. And what this duty cycle is it says we have a number of different events. and they're all in the time domain. So we have time series data like we looked at before, but multiple events. As a matter of fact, we even have repeats with them. So I have 4 different events and different repeat counts for each one that makes up the mix, or the durability schedule, or the duty cycle for a full life of this particular part. This data file I picked up, the duty cycle file here, it's called a .dcy file. That was created using this module, this app over here called Schedule Create. I'm not going to use that right now because if I do that, then we'll run out of time. But I would encourage you to look at that. And as a matter of fact, when we're done here, I'll show you how you can retrace all these steps today through DesignLife worked examples. I'll show you a resource for that in just a bit. So the key thing here is now I'm working with a duty cycle, and I'm going to calculate damage for each of these events and then increase the damage or multiply the damage by the repeat count and then add them together. So this is just being smart about Miner's rule. So notice now that I no longer have a blue or time series input to the fatigue calculation glyph. I don't need this time series data any longer. I'm going to delete this glyph because I've told the analysis here that it's built on this duty cycle that I created earlier, that mix of different events. When I run this, it's going to take a little bit longer than before because it's actually got to calculate fatigue over different events. But the cool thing is that now my fatigue life here, these results, if I look at them, let's just take a look and see what results are available. We have fatigue results now for a combined duty cycle. So now this is looking at life. It's saying that our life is a minimum down in this region here, a minimum of about 1,200 repeats. Well, repeats of what? Repeats of that duty cycle. We have various ways we can post-process those fatigue results. We're looking at the combined damage from all of the events together. So how many duty cycles to failure? We'll look in just a minute at breaking this down into understanding which events provided how much damage. So which of those 4 or 5 events, different ways of driving, different ways of using this component, which ones were really most significant in a fatigue sense. So that's a quick introduction to a couple things, looking at peak valley extraction to speed up time series, looking at multiple runs, a stress assessment, as we looked at, focusing on hotspots. By the way, I didn't mention this, but I will now. My computer's got 8 cores here, so it's using that to its advantage as well. What I want to do now is shift out of building a process and actually show you something with a full vehicle. This is a process to do to look at this entire white body here. Look at this entire white body and calculate fatigue on it. This is I think this is about 500,000 elements, so it's a little bit smallish. It's a couple years old, so your particular white body might be bigger than this by a factor of 2 or 3 or something. I've already built this process and run it from before this webinar just because it takes about 3 or 4 minutes to run, which doesn't sound like very long, but it seems like eternity when we're all just sitting waiting for it to go. So what this process is doing is it's really built on all the stuff that we've talked about so far. For example, if I look in here, let's take a look at this process here. This has actually got 3 different runs. So the first run that it does is looking at stresses alone, not fatigue. So it's going to go off and find, it's going to keep 25% of the model based on stresses. So very quickly, it'll get rid of 75% of the model. This is really, really nice because it gets rid of a huge amount of calculation requirement very quickly. It passes that off to the second calculation. The second calculation is going to do fatigue now. It's built on working with a duty cycle. So if I look at my loading up here, I've got this idea of a duty cycle with all these different events as well, just like we looked at with the simpler model just a minute ago. We have all these events and different repeat counts and such. This first fatigue calculation on the hotspots is going to use a very aggressive peak valley gating technique. In other words, it's going to take the time series data and use a very large peak valley gate. What that means is the time series data being squiggly, it's going to remove non-turning points, and even further, it's going to remove a lot of cycles, which you may say, hey, hang on, time out. If you're removing a bunch of cycles, then non-conservatively, we could be removing a lot of damage. And that's fine, because all we're going to use this pass for is to find hot spots not of stress. We've already done that. We're finding a further reduced set of hot spots of high fatigue damage, or high fatigue damage as an approximation, a quick approximation using this very aggressive peak valley gating technique. This then passes 1,000 elements, the highest 1,000 elements of fatigue damage, into the third run. The third run sits down here. And notice now that this one has a peak valley with a very small gate, or to be absolutely technically correct, we may wish to turn off peak valley extraction entirely. The beauty of this is, since we're only analyzing only 1,000 remaining high damage, high stress elements, we can do some really complicated, fully featured fatigue stuff here and still have a reasonable amount of time. What we don't want to do is use a fully featured, computationally intensive fatigue analysis method on the entire model, or even a large portion of the model, because that's calculation time. It's going to take a lot of calculation time. The results we get here, we have shown in a plot here. This is showing of looking at a couple hot spots. Remember, we have only 1,000 elements actually having this final fatigue calculation being done on, so we don't have a lot of colored stuff going on here. I've got what's called a hotspot detection concept running here, so it'll point out to me of the however many calculation points it used. Here are the top 10 different areas of high fatigue damage or low fatigue life. Furthermore, the calculation results are being shown here in this table. So similar information, but we can see now this has got fatigue life and fatigue damage presented in a tabular form. That table, what's kind of cool is I can take that table and run it through this glyph here called % by event. And what this will do is, since we're using a duty cycle, the answers we were looking at before were total damage, Miner's rule, total damage sum. And you may wonder then, okay, so we had all these different driving conditions, and which ones of those actually influenced or contributed most to damage? This glyph called % by event will take these duty cycle results and recast them in kind of an interesting way. Now we have in each row an element with highest fatigue damage sorted down to lowest, and then the % of damage that comes from each of these events. So this is just allowing us to, you could say, dig into Miner's rule a bit. Miner's rule returned a sum that said the total fatigue damage is this. And by the way, as you can probably guess, we have a fatigue problem on our hands here, because it says the highest fatigue damage is 1.6. In other words, we won't even be able to complete a full duty cycle, say 150,000 mile life, before failure. So we've got a pretty critical fatigue hotspot here. And if we do, we may then wonder, what's driving that fatigue? What fatigue cycling drives that fatigue damage problem? Well, this % by event calculation now tells us of the different events, which ones produce how much damage. And you can see right off the bat that event A and event B are not significant in a fatigue sense. It's something about events C, D, and E that are really critical. So this is not necessary. This type of % by event calculation is not necessary to improving the speed of this fatigue calculation. But since we're using a duty cycle to speed up this calculation, Miner's rule and this % by event together can be very useful to look at. And that's why I've introduced this % by event glyph. Now, one last thing before we switch into questions and answers, and that is to point out, just if you go down here in the lower left corner in the manuals, you'll find our PDF doc set, including DesignLife work examples. Make sure this is shared here. There it is. Okay, and the reason why I'm pointing this out is that if you haven't seen this yet, this is a wonderful resource if you like to read and learn what DesignLife can do. We have 23 chapters of how to do things in DesignLife, and some of these are directly applicable to what we've looked at today. For example, let's see here. if you wanted to learn about seam welding, how can we apply specific welding methodology for fatigue, then this chapter might be useful to you. Running DesignLife in batch, if you want to go off and send this off, run this in batch on a Linux box or something like that. That might be useful for you to read about this. Here's transient analysis using modal transients. We talked about this as being an efficient technique for working with long time series data, but still accounting for dynamics without having to rely on a direct transient, instead using a modal transient. So this will step you through how to build that process. And also we have other things here like how to look at duty cycles. One of these in here is working with duty cycles, and so on. So I encourage you to look at this. This may help you in trying to replicate some of the things that we've looked at in our calculation today. So with that in mind, just want to